In the last video, we talked about the techniques we could use to solve for unknown side lengths and angle measures in a right triangle. So based on what we know, based on what we don't know, we set up a ratio using one of our trigonometric functions, and we could use that ratio to either solve for an unknown side length, assuming we have a given angle, or to solve for an unknown angle, assuming we have two side lengths in our triangle. Everything we've looked at so far from a trigonometric standpoint has been dependent upon having a right triangle. So in the last video, all of the situations where we were able to draw a picture for an application, all of the pictures we drew had a right triangle somewhere contained inside of them. And in fact, our trigonometric ratios are all defined in terms of right triangles and how our sides relate to the angles in the triangle. What happens though if we no longer have a right triangle? So what if we're in the context of a situation, but that situation cannot be represented by a right triangle, which means we no longer can define those side ratios in relation to our angles? All of those things we've talked about so far are very much dependent upon the fact that we are inside of a right triangle. What happens if we're not though? So what we're going to talk about in this video and in the next video are the techniques that we use when we want to solve a triangle that doesn't contain a right angle. So a triangle that does not contain a right angle is what we call an oblique triangle. And an oblique triangle is going to fit one of two different patterns. So one possibility for an oblique triangle is that all of the angles are acute angles. All three angles are acute angles, which just means they're all less than 90 degrees in terms of their angle measure, and no obtuse angles. Obtuse angles have a measure greater than 90 degrees. So that's one possibility. Now another possibility is that two of the angles are acute angles, and then one of the angles is going to be greater than 90 degrees. It's going to be an obtuse angle. So anytime we have a non-right triangle, an oblique triangle, it's going to fall under one of these two cases. So in this video, we're going to talk about a couple of different situations in terms of how we can be given information about an oblique triangle and use that information to solve for anything left in the triangle that's unknown. So we're going to use what we call the law of sines, which is going to relate to our sine function. Now we know in a right triangle, the sine is defined for each angle as the ratio of its opposite side over its hypotenuse. So sine still means the same thing, but in the context of these kind of problems, we're just going to evaluate our sine values in the calculator. So sine still means the same thing, but we're using it in a slightly different way. So suppose we have a triangle that we're going to call ABC. Now in this case, C does not necessarily represent the hypotenuse. If we're talking about an oblique triangle doesn't have a hypotenuse. A, B, and C are just angles, and then little a, little b, and little c are just side lengths opposite those angles. One does not have to be related to another in a specific way in the sense that one's always the longest side. These are just arbitrary labels for angles and their opposite side lengths. The following is the relationship expressing the law of sines. So if we were to take the sine of any angle, for instance angle A in the triangle, and divide it by the length of side A, that ratio is going to be the same if we were to repeat the process for angle in side B and then also angle in side C. So what the law of sines tells us is that the ratios of sines to opposite side lengths is constant for any pair in the triangle. So we're going to use the law of sines in specific cases where we have a known side angle pair. If we have a side and the angle that it's opposite, then we can use the law of sines to solve for anything that's unknown in our triangle. So why is this? Well, if we have an angle and then the side that's opposite it, we can define that ratio that's going to be constant for any pair within the triangle. So having this side angle pair, or being able to quickly find the side angle pair, is going to allow us to use this constant ratio to set up relationships among all the sides and all the angles, and thereby solve for whatever happens to be unknown. So let's look at the first case in terms of information that we could be given structured in a specific way. So case 1 is going to be side angle angle or angle angle side. This just means we're given a side, an angle, and an angle in that particular order if we were to label the triangle. So 2 angles given, and then a side is given as well. Now, how do we know that this represents having a side angle pair? It's going to be easier to see once we label a triangle. And knowing what case we fall under is not going to be all that important. What's going to be important is labeling the triangle and then identifying that pair so that we can apply this law of sines. So we want to solve the triangle, which just means find all side lengths, find all angle measures, where angle A has a measure of 31 degrees, angle C has a measure of 76 degrees, and then side C has a length of 19 units, whatever those units are. So you'll notice I've drawn what looks like an equilateral triangle. This is just an arbitrary triangle drawn so that we have something to label. We have some type of visual. But just based on the angles we have so far, already we can tell that this triangle is not to scale. This triangle does not actually reflect the values we have in this problem. All this is a picture that will allow us to label and determine the relationships among our sides. So it's going to all be about labeling. Just like in the last section, I said your artistic skills don't matter. It matters that you interpret, draw the diagram correctly, and label things. Labeling is going to be what's important here. So we need to label our angles. It doesn't matter which order you label them in. My advice is just pick an order and be consistent. So I typically label angle A up top, and then I'm going to label B and C in this way. Now, once I've labeled in this order, I'm committed to where these side lengths are. So side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. And again, side C does not necessarily, or angle C does not represent a 90-degree angle. Side C does not represent the hypotenuse. These are just arbitrary labels. So based on this and based on the information we're given, let's label what we know. So angle A has a measure of 31 degrees. Angle C has a measure of 76 degrees. And then side C has a length of 19 units, whatever our units happen to be. And we want to solve for anything that's left. So in this case, angle B, side B, and then side A. Now, how do we know we can use the law of sines? We know we can use the law of sines because of this. Notice we have an angle and an opposite side pair. So what that means, if we have angle C and side C, it means we know the value of this ratio. And if we know the value of this ratio, we know based on the law of sines that that value is going to be constant for any pair that we would create within this triangle. So having that constant pair is going to allow us to set up some relationships with our unknowns that will allow us to solve for those unknowns. So where do we start? What do we solve for first? Well, we can actually solve for angle B without any trigonometry, without the law of sines. Why is that? Well, we know that in any triangle, the angle measures have to add up to 180 degrees. So that's true for a right angle or a right triangle. It's true for any other triangle as well. So here, because we already know 2 angle measures, we can solve directly for B just using that relationship. So angle B is going to be equal to 180 degrees minus the 2 degree measures we were given. So 31 degrees and 76 degrees. So 180 minus 31 minus 76, and that's going to give us 73 degrees. And we can label things as we want, or you can just keep working from there. So I'm going to label that. That's going to be 73 degrees. And let me box this in because this was something we solved for. It's a good idea to make a note of what you solved for versus what you were given, because as I mentioned in the last video, ideally when we're solving for new things, we want to use givens rather than things we solved for as much as possible, just to avoid the possibility that we made a mistake early on and we propagate that mistake through the problem. So that is going to be angle B. Now it's a good idea to go ahead and think about how the sides are going to relate to the angles in terms of the size. So in this case, angle C is going to be the largest angle, which means the side opposite that is also going to be the largest side. Angle A is going to be the smallest angle, which means side A is going to be the smallest side. So as we've solved for these additional unknowns, specifically side A and then side B, it's going to be important to keep that in mind in order to know whether or not our answers actually make sense. So normally we can just go alphabetically. A good rule of thumb is start with the smallest angle and smallest side and work your way smallest to largest. So angle A in this case is the smallest angle, which means side A is going to be the smallest side as well. So here's what I'm going to do in order to use the law of sines. I'm going to start with the pair that I'm given. I was given angle C and then the side opposite that, side C. So I'm going to write the ratio of the sine of angle C divided by side C. So the sine of 76 degrees divided by 19. Now, whatever that number happens to be, I know that that number is going to be constant for every pair in the triangle. And so if I want to solve for side A, I'm going to relate side A, which is given, side A, which we don't know, to angle A, which is given. So I'm going to write the ratio of sine of A to side A, which we don't know. So this constant ratio is also going to be equal to the sine of 31 degrees divided by our unknown, which is side A. So now I can solve for A, and I'm going to write out the details for this one example, and then we'll kind of skip some of the details after that. How do I actually isolate A in this case? Well, one good option here is to just cross multiply. That's a good place to start. So anytime we have two ratios and they're equal, we can cross multiply, and that's one way to sort of clean things up and simplify things, and more specifically get rid of the denominators. So I'm going to multiply both sides by A, which moves the A over. So A times the sine of 76 degrees. And then I'm going to do the same thing for 19, move it over. So 19 times the sine of 31 degrees. And then A, again, we want to isolate that, so I'm going to divide by the sine of 76 degrees, move that over, and that isolates my A. So A is equal to 19 times the sine of 31 degrees divided by the sine of 76 degrees. Whatever that happens to be, sine of 31 is a number, sine of 76 is a number, so all of this is just a number. And I can get that by plugging it into the calculator. And we want to round to 1 decimal place. So 19 times the sine of 31 degrees divided by the sine of 76 degrees. And of course, double check that you are in degree mode before you do anything further. And there we go, that's what we get. So to 1 decimal place, approximately 10.1 units. So side A, approximately 10.1 units. Now, does this make sense? Well, remember, this is going to be the smallest side, so at least it's smaller than the side we're already given. So far this makes sense. That means side B should have a length somewhere between 10.1 and 19. Now, in terms of solving for side B, you may be looking at this and thinking, well, I've got two sides, I can use the Pythagorean theorem. You cannot use the Pythagorean theorem here. Why can't you? This is not a right triangle. The The Pythagorean theorem only applies to a triangle that contains a right angle. So because this triangle doesn't contain a right angle, the Pythagorean theorem doesn't actually apply to it. So in order to solve for side B, essentially we're going to do the same thing we did right here. We're going to use that constant pair that we were given, write that ratio, and then relate angle B to our unknown side B. So essentially it's going to look basically the same as what we have here, but we're relating angle B and side B. So our constant pair, what we were given, sine of 76 degrees divided by the opposite side length, which is 19, is equal to the sine of angle B, so sine of 73 degrees divided by our unknown side B. And again, just for the sake of actually showing you the algebraic steps to isolate your B, let's go through it in detail this time. So multiply both sides by B, multiply both sides by 19, so that we get rid of these denominators. So B times the sine of 76 degrees is equal to 19 times the sine of 73 degrees. We divide sine of 76, move that over, and so B is equal to 19 times the sine of 73 degrees divided by the sine of 76 degrees. And then we're going to approximate that to 1 decimal place. And because B is the angle in the middle in terms of measure, it's not the smallest, it's not the largest, the side length should also be somewhere between the smallest and the largest. So let's verify that. So 19 times the sine of 73 degrees divided by the sine of 76 degrees. And so to 1 decimal place, that's going to be 18.7. So side B has a length of 18.7 units. And again, it's smaller than 19, larger than 10.1. Notice it's close to 19, but that's because the angles were also pretty close in size as well. So it makes sense that the side lengths would be close in basically the same fashion. So that's the general idea, and that's essentially the general idea with any law of sines problem. The only thing that changes is how we're given information and the structure of the resulting triangle. So let's look at the next case. The next case is being given an angle and then a side and then an angle in that order if we were to draw the triangle. So we want to solve the triangle where angle A is equal to 132 degrees, angle B is equal to 28 degrees, and then side C has a length of 6.8 units. And again, we want to round the lengths of the sides to 1 decimal place. Notice it doesn't say anything about rounding the angle measures. That's because as of right now, we can solve for those angles exactly just using that 180 degree relationship. So again, start by labeling the triangle A, B, C. We were given that angle A was 132 degrees. We were given that angle B is 28 degrees. And then we were given that side C, little c, is going to be 6.8 units. Now, looking at this triangle as it stands, we don't have a side angle pair. So it almost looks like maybe the law of sines doesn't apply. But notice we can directly solve for C just using that 180 degree relationship. So let's start there and let's see where that takes us. So angle C is going to be 180 degrees minus the angle measures already represented. So 132 degrees and 28 degrees. So 180 minus 132 minus 28, and that's going to give us 20 degrees. So angle C has a measure of 20 degrees. So we solved for that directly, no trigonometry was involved. And notice now we have the side angle pair. So as soon as we have that pair, we can set up all those relationships involving the law of sines. So angle C related to side C, specifically the sine of angle C, so the sine of 20 degrees divided by 6.8. Whatever the value is for that ratio, that's going to be constant for every pair in the triangle. So let's start with angle B in this case because it's the smaller of the two remaining angles. So angle B in relation to side B. So our ratio is going to be the sine of angle B divided by the length of side B. So the sine of 28 degrees divided by the length of side B. Now because angle C is the smallest angle, side C will also be the smallest side. Angle B is a little bit bigger, so we expect side B to also be a little bit bigger. So if you need, take a moment, pause the video, make sure you can isolate B. You'll get to the point where you'll probably start to see the pattern in how anything like this is isolated. So we're moving the B over, we're moving the 6.8 over, and then we'd have to divide by sine of 20 degrees. So that's going to be 6.8 times the sine of 28 degrees once we move the 6.8 over. And then all of that is divided by the sine of 20 degrees. And so rounded to 1 decimal place, that's going to be 6.8 times the sine of 28 degrees divided by the sine of 20 degrees. And so to 1 decimal place, that's going to be 9.3 units. So angle B, opposite side B has a length of 9.3 units. Again, it makes sense. We should have a side length larger than the length of side C because angle B is larger than angle C. Now, again, if you're tempted to use the Pythagorean theorem, don't. You can't use the Pythagorean theorem here. We don't have a 90-degree angle. The Pythagorean theorem doesn't apply. So we repeat the law of sines, again, using that pair that we now have. So sine of 20 degrees divided by the length of the opposite side, which was 6.8, is equal to the sine of our remaining angle, angle A, 132 degrees, divided by the length of side A. So sine of 132 degrees divided by side A. We isolate A. So A, move it over, multiply both sides, move the 6.8 over, and then divide by that sine of 20 degrees. So A is equal to 6.8 times the sine of 132 degrees divided by the sine of 20 degrees. And I can't encourage you enough, don't try to memorize how things move around. If you need, take a minute, pause the video, and make sure you can manually move things left to right and make sure you end up with the correct ratio for your unknown. And so plugging that into the calculator, 6.8 times the sine of 132 degrees divided by the sine of 20 degrees. And we get about 14.8 units. So as expected, the largest side is opposite the largest angle. And so there's our values there. So this particular case, angle, side, angle, and then our previous case, side, angle, angle, or angle, angle, side, depending on your point of view. Notice in both of these cases, we were either given a side angle pair to start with, or we could solve for one. But more importantly, we were able to directly solve for whatever angle was left. So if we're given two angles in any sort of combination, we can directly solve for the remaining angle using that 180-degree relationship. Well, what if we don't actually have two angles to start with? Well, if we don't have two angles to start with, we're not going to be able to use the 180-degree relationship to solve for whatever angle or angles are left. We're still going to use the law of sines, but we're going to use the law of sines not only to solve for side lengths like we did here and did in the last example, but also to solve for angle measures. This presents an additional problem that we're going to have to deal with. So the next case we look at is what we call the ambiguous case. Once we start solving for an angle using the law of sines, we run into some potential for different things to happen depending on the actual numbers in the problem. So side-side angle, and you can probably guess why we don't call it angle side-side, we call it side-side angle, is the ambiguous case. So ambiguous in the sense that any information we're given about a triangle that will be structured like this could define one triangle, exactly one. In other words, there's a unique set of solutions for each of the unknowns. It could also define two different triangles, and I'll show you why in just a minute. Or technically, it could define no triangle at all. So we may have values given, and we may be able to draw a triangle to start with, but it may turn out that that particular combination of values can't actually exist within a real triangle. So where does this uncertainty come from? The uncertainty comes from the fact that, again, we cannot directly solve for the remaining angles using that subtract from 180 degrees technique. So we're always going to start a problem like this by solving for the paired angle. What do I mean by that? Well, once we draw the triangle, you're going to find that the angle you're given pairs up with one of the sides you're given. So that means you have one additional side left. Well, the only thing you can solve for is going to be the angle opposite that additional side. So we always have to start by solving for whatever that paired angle is. And we're going to use inverse sine to solve for the angle. So we know when we evaluate a trig function, we plug in an angle and we get out unit circle coordinates, a ratio for a right triangle, something like that. If we want to generate an angle instead, if the angle is what's unknown and we want to solve for the angle, that's when we're going to use the inverse trig function, in this case the inverse sine. Using the inverse sine is where we run into issues where we potentially can have different things happen with these particular problems. So we're going to look at one example of each type. So a situation where our values define a single triangle, a situation where our values could actually represent two different triangles, and then also a situation where we don't actually have a triangle at all. Those values couldn't actually exist within a real triangle. So I've labeled them. We know what to expect. Now we just have to determine why do we expect these things to happen? How do these problems arise? So for our first example, this is going to be a one solution situation. In other words, we can draw a triangle with these measurements and only one such triangle exists. So all the unknowns we find, there's only one combination of unknown values that would actually make the other values that we have fit together. So we were given that angle A is 57 degrees, its opposite side is 62 units, and then side B is 50 units. And we want to round the measures of the angles, we're going to have to round those too, and the unknown side to 1 decimal place. So let's label the triangle, and then we'll go from there. So angle A we were given was 57 degrees. Side A is 62 units. So automatically we know there's our pair. That's going to be the pair we use. Now side B is 50 units, and we don't know anything about either of the C's. Now because we don't know anything about either of the C's, that locks us into the only unknown we can find, which is going to be angle B. So angle A to side A, angle B to side B. This is the only thing we can solve for based on the fact that both of the C values are unknown. So let's set up the ratio. But now we have to keep in mind that the angle is not given, the side length, the opposite side length is what's given. So our constant pair, the sine of 57 degrees divided by the length of the opposite side, which is 62, and that's going to be equal to the sine of our unknown angle B divided by the length of the opposite side, which is 50. Okay, so here we can immediately isolate the sine just by moving the 50 over. So we have sine of B is equal to 50 times the sine of 57 degrees divided by 62. And then in order to solve for the angle, for the unknown angle, in order to eliminate the sine, we take the inverse sine of both sides. So taking the inverse sine on the left eliminates our sine. And then we also apply it to the right-hand side to keep things in balance. So B is equal to the inverse sine of 50 times the sine of 57 degrees divided by 62. Now this looks very complicated, but you're just going to plug it into the calculator, so just go step by step. Now I strongly encourage you, do not try to type this whole thing in one line. Go step by step. So maybe just start with what's inside parentheses. Just type all of that. So 50 times the sine of 57 degrees, and we're dividing that by 62. Okay, so that is now the number in parentheses, and you don't need to write it down, you can keep working. We're now taking the inverse sine of that value. So inverse sine, right above sine in blue, so second and sine, inverse sine. And we're plugging in this previous value into the inverse sine. So I'm going to copy that answer from the previous line. So second and negative copies the answer. And then I hit enter to evaluate. And so that's going to give me, to one decimal place, approximately 42.6. And now we're talking about degrees. Okay. This is where we potentially run into a situation where we go from one solution to potentially two solutions. So what's the problem here? Well, think about what happens with inverse sine. So when we originally introduced the inverse sine function, we had some issues with the original sine function, so we limited the angles we could get when we evaluate the inverse sine function. So every time we evaluate an inverse sine, we either get an angle in the first quadrant, something between 0 and 90 degrees, or something in the fourth quadrant, a negative angle, something between negative 90 degrees and 0 degrees. So that essentially throws away a couple of the quadrants on the unit circle. But that actually creates a little bit of a problem. So I'm going to draw just the top two quadrants of the unit circle. And I'm not going to draw necessarily the circle. I can if I want. If it makes you feel better, let's do it. And let's draw 42.6 degrees. So that's essentially right about there. Okay, so we're talking about that particular angle. So that is 42.6 degrees. So what we're saying is at that particular location, the y coordinate, the sine, has a value of about 0.676. Okay. Notice also though, in the second quadrant would also give us angles that have sine values that are positive. So there's another angle, it happens to be a second quadrant angle, something between 90 degrees and 180 degrees, that also has this 0.676 roughly as the value for its sine. It's whatever angle we would get that's symmetric on the other side. So it would be this angle. That angle has the same value for sine, which means it would also potentially satisfy this relationship. Well, what is that angle? How do we know what that angle is? If both of those angles satisfy this relationship, well, what is that other possible angle? Well, we know if they have the same trig values, they have the same reference angle, which means that this angle has to be the same as 42.6 degrees. So the other possible angle, the other possible value for B is going to be 180 degrees minus 42.6 degrees. Whatever that angle is, it has the same value for its sine, and will potentially represent another value for B that solves this problem because they have the same trig values. So another B, question mark B, maybe B, is equal to 180 degrees minus this angle we just found from our inverse sine, which is 42.6 degrees. So if we take 180 and subtract that, 180 minus 42.6 degrees, that's going to be 137.4 degrees. If we were to take the sine of 137.4 degrees, notice we get roughly 0.676. So 42.6, the value we got from the inverse sine, and this other value, 137.4, both have the same value for sine. So they're both potential values that could solve our triangle. So how do we know whether or not this does work? Which one's right? Is one of them right? Is one of them wrong? How do we know? Well, 42.6 degrees, we need to determine, could this actually fit in the triangle we have? Well, all we know so far is that our triangle has a 57-degree angle, which leaves us with a bunch to make up in order to get to 180 degrees. Well, 42.6 degrees added to 57 still fits within that limit of 180 degrees. So 42.6 degrees is a possible solution because it still leaves us enough room to have an angle C in order to add up to 180 degrees. But what about the 137.4? If you were to take 137.4 degrees and add it to what we currently have represented in the triangle, which is 57 degrees, notice it adds up to 194.4. In other words, it adds up to something greater than 180 degrees. So because this angle can't be combined with what's already in the triangle, because it adds up to more than that 180 degree limit, that is our indication that this is not a possible value for B. So although it is another angle that meets this requirement, that has that particular value for its sine, it cannot fit in this triangle based on the relationships we have in this triangle and based on the information we know already. So this is going to be the specific value for B. That's our indication that there's one solution. Since there's only one value for B, the one solution is going to be all the other values that result from taking that one value for B. So B is going to be 42.6 degrees. Now once we have that, we now have enough information to solve for angle C. So we have a given angle, we have the angle we just found, we can solve for C with that 180 degree relationship. So C is equal to 180 degrees minus the 57 degrees that we were given, minus 42.6 degrees, what we just found for B. So 180 minus 57 minus 42.6. And that's going to give us 80.4 degrees. So angle C has a measure of 80.4 degrees. So based on that, what do we know about the side lengths? Well, the smallest angle is 42.6 degrees, angle B, so it's going to be opposite the smallest side. Angle A is bigger, so its opposite side is also bigger. Angle C is the largest side, so that means side C should be the largest side. Now remember, no Pythagorean theorem, this is not a right triangle, so we use the law of sines again, but now we're using it to solve for a side, which is what we did in the previous examples. So using that pair that we were originally given, so sine of A, which is sine of 57 degrees, divided by the opposite side length, which is 62, is equal to the sine of angle C divided by its opposite side. So the sine of 80.4 degrees divided by the opposite side length, side C. So we isolate C, move it over, move the 62, divide by sine of 57. So 62 times the sine of 80.4 degrees divided by the sine of 57 degrees. And whatever that is side C. So 62 times the sine of 80.4 degrees divided by the sine of 57 degrees. And to one decimal place, approximately 72.9 units. So little c, approximately 72.9 units. And as we expect, largest angle, opposite side is also the largest. Now, one thing to keep in mind here that's a little bit different, in addition to this issue of using the inverse sine to solve for an angle, because we had to round the value for this angle, additional rounding occurred and propagated throughout the problem. So we rounded angle B, and then we had to use that rounded value in other locations in the problem. So angle B was rounded, which means that when we found angle C, yes, angle C, angle B, and angle A add up to 180 degrees. But because B was rounded, C also resulted from that rounding. So C is the exact in the sense that it relates to the other angles in terms of adding up to 180 degrees, but this value was generated from a rounded value. And then side C, we rounded at the end, but side C also resulted from a rounded value. So we do need to keep in mind that the rounding does propagate. So pay very close attention to the rounding directions. If it says round intermediate answers to a specific number of decimal places, maybe more than one, make sure you follow those guidelines, because as we round in the middle of the problem, the rounding affects things towards the end of the problem as well. So just be mindful of that kind of thing. Okay, so let's look at the next possibility. The next possibility is we have the same setup within the triangle, but the values that we have given don't actually represent a possible triangle. So let's see what that would look like. So we're given that angle C has a measure of 39 degrees, side C is 6 units in length, and side A is 15 units. And again, we want to round our unknown angle measures and our side lengths to one decimal place. So angle A, angle B, angle C. We were given angle C, 39 degrees. We were given side C, 6 units. And then we were also given side A, which is 15 units. So here's our pair. We don't know anything about either of the B's, which means the only thing we're capable of solving it for in this moment is going to be angle A, since we have its opposite side. So writing our ratio, sine of 39 degrees, the given angle, divided by the opposite side, so that's going to be our constant pair. That's going to be equal to the sine of unknown angle A divided by side length A, which is 15. Now to start with, because side A is bigger than side C, we expect angle A to be bigger than angle C. So the relationship works both ways. So in theory, when we solve for angle A, it should have an angle measure that's bigger than 39 degrees. So let's see what's going to happen here. So we can isolate sine A in one step. Just move that 15 over. So 15 times the sine of 39 degrees divided by 6. And then again, we're solving for an angle. We need to get rid of the sine, which means we're going to apply the inverse sine to both sides of this relationship. So A is going to be equal to the inverse sine of all of this. So 15 times the sine of 39 degrees. And that's going to be divided by 6. So just like with the previous example, don't try to plug all this in at one time. It's a bad idea. Plug in a little bit at a time. Just start by evaluating the expression inside the inverse sine. So 15 times the sine of 39 degrees divided by 6, and that's going to give us about 1.6, and so we're taking the inverse sine of that. Now, as soon as I see that, a red flag pops up. What's the problem with this? Well, remember when we defined the inverse trig functions, we plug in a value for sine, cosine, or tangent, and we get out the angle, a specific angle that would give us that value. So what we're asking, if we're evaluating the inverse sine of this number, is we're asking what angle has this value as its sine. Well, if you remember, if you look at the unit circle, the lowest number you can get in terms of a sine value, a y value on the unit circle, the smallest value is a -1, and then the largest value you can get as a y coordinate, as a value for sine, is going to be the value +1. So we're saying we've found an angle that has a sine of 1.6. What is the angle? Well, in theory, there isn't one that exists, right? If everything is defined based on the coordinates of the unit circle, and the unit circle caps out at -1 and 1, there's no way we can get a coordinate of 1.6, thereby representing the value for our sine. So in theory, there is not an angle that will represent this particular value for sine. So what's going to happen when we take the inverse sine? So I'm going to take the inverse sine, copy my answer from the previous line, and what happens? I get an error. I get a domain error. That means that this value that was plugged into the inverse sine doesn't exist within the inverse sine's domain. Remember, when we defined the domain, we said we can only plug in numbers from -1 to 1 because those are the only values the sine function can take on. We can only get angles from the values that sine can actually take on. So because we run into that error, this does not exist. A does not exist. That means there is no solution to this triangle. Although it looks like we can label and create a triangle with these particular values, we can't, because what we end up with is something that violates the rules for our trig function and for its associated inverse trig function. So that's kind of a special case. Now, can you just look at the problem and tell which case it's going to be? Unfortunately, no. So you want to start by drawing the diagram, labeling everything, setting up that ratio relationship, and then you go from there. Once you get to evaluating that inverse sine, that's going to indicate that there is no solution because you run into that error in the calculator. You get something that's outside of the domain of your inverse sine function. So our last possibility is that we can solve the problem. There is a solution. It's not no solution, but there's not a unique solution. There's actually two different solutions. And so it's going to be similar to that first example we worked under the ambiguous case, but whereas at the step where we determined the other angle that would have the same value for sine, whereas it didn't work here, it couldn't fit into the triangle, it's possible that it will fit into the triangle. And that's what's going to give us the two possible solutions. So we want to solve this triangle that has an angle measure A of 29 degrees. Side length A is 7 units, and side length B is 10 units. Now, start by assuming it's just one triangle, because in most cases it will be just one triangle. So I'm going to label my triangle A, B, and C, and we were given angle A is 29 degrees. We were given side A is 7 units, so there's our pair, and we were given that side B is going to be 10 units. So here's the pair that I'm given. I don't know anything about the C's, which means angle B is the only thing that I can solve for at this point in the problem. So using the law of sines, we know that the sine of 29 degrees divided by the opposite side length, which is 7, is equal to the sine of angle B divided by the only additional value we know, which is side B, which is 10. Okay, just like with the last two examples, isolate the sine. So sine of B is equal to 10 times the sine of 29 degrees divided by 7. And then in order to isolate B, eliminate the sine function, we apply the inverse sine function to both sides. So all of this now becomes the input for that inverse sine function. Well, let's plug it into the calculator and let's see what happens. So start with everything that's on the inside. So 10 times the sine of 29 degrees divided by 7. Okay, so we at least have something that's less than 1. So remember, the issue we ran into with the previous example was we evaluated this kind of expression and we got about 1.6, something that can't represent a value for sine. Well, as long as we get a number that's between -1 and 1, then we have something that could represent a value for sine, and that means this angle is going to be defined. So I'm going to take the inverse sine of this value, and that's going to give me, to 1 decimal place, approximately 43.8 degrees. Now, as with the first example we looked at, picture what that looks like. That looks something like this, pretty close to what we had. Pretty close angle, right? That means there's also an angle in the second quadrant that has the same y coordinate and therefore has the same value for sine. If they have the same trig values, they have the same reference angle, which means these two angles will be the same, and it means the additional angle we want is going to be the half rotation, 180, minus that particular value, which is the angle we solved for. So the other possible value for B is going to be 180 degrees minus 43.8 degrees. So 180 minus 43.8 is going to give us 136.2 degrees. So now we have a dilemma, same kind of dilemma as before. If we were to take the sine of 136.2 degrees, well, we get 0.692, basically the same thing we got before. We get essentially this value, which means this is also an angle that would satisfy this relationship. So it has the right sign in order to satisfy this relationship, but could it fit the triangle? Can it actually fit in the triangle? Well, if you look at the angle measure we already have, we have an angle measure of 29 degrees. So 43.8 degrees and 29 degrees, that still leaves us room to solve for an additional angle. 136.2 degrees and 29 degrees also still leaves us room to solve for an additional angle. In order to verify that, let's take those and add them up. So 136.2 plus the 29 degrees we already have, that only takes us to 165.2. It's still less than 180. There's still room for an additional angle in the triangle. So that means both of these are possible values for B. That is where we end up with two solutions. What that really means is that this set of information actually matches up with two different triangles. For one of them, B is an acute angle, and for one of them, B is an obtuse angle. So what's going to change from one triangle to the next is which angle in the triangle is largest, and therefore which side in the triangle is also going to be the largest. So we're going to label one triangle with our smaller value of B. So for triangle 1, we're going to allow B to be the acute angle, the one we got from the inverse sine function. And then for triangle 2, we're going to evaluate the additional values using the other value for B, using the obtuse value for B, which means we need to go ahead and label another triangle. So this is going to be A, this is going to be B, this is going to be C. Our given information is still the same. So A is still 29 degrees, little a is still 7 units, and then little b is still 10 units, and we still use the same pair. The only thing that changes is the value for B. So for our first triangle, we're using the value for B that resulted from our inverse sine function. And then for the second triangle, we're using that other angle, that second quadrant angle, the one the inverse sine didn't identify, but an angle that also has the same value for sine and can also fit the relationships that need to be fit in this particular triangle. So 132 or 136.2 degrees, also going to represent a triangle. Okay, so what does all of this mean though in the context of the numbers in the problem? Well, for triangle 1, 29 degrees is our smallest angle. It's going to be opposite the smallest side. 43.8 degrees is going to be the next largest angle because C clearly has to be larger than those two. So this is going to be the side that's in the middle, and C will be opposite the largest side. For this triangle, angle B is going to be the largest angle. If we have an angle that's an obtuse angle, that's the only one we have in the triangle. Every other angle is going to be an acute angle. So this particular angle is going to be opposite the largest side. In this case, 10 is going to be the largest side in the triangle. So the other two sides are going to have to be smaller in proportion to one another. So let's start with our first triangle. What do we still need? Well, we need angle C, and we also need side C. Now, because we have two angles at this point, we can solve for C directly. So C is going to be 180 degrees minus 29 degrees minus that value of B we just found, which was 43.8 degrees. And so we evaluate that in the calculator. So 180 minus 29 minus 43.8, and that's going to give us 107.2 degrees. So that's going to be the value of C that results from this particular value of B. So notice in this triangle, C is the obtuse angle, it's the largest angle, whereas in the second triangle, B is going to be the largest angle. Well, if C is the largest angle, we know side C is also going to be the longest side, and we find it again using the law of sines. So using the angle and the side we were given, so sine of 29 degrees divided by 7 is equal to the sine of our angle C divided by the opposite side length. So sine of 107.2 degrees divided by our unknown side length C. So isolating C, we get that C is equal to 7 times the sine of 107.2 degrees, all of that divided by the sine of 29 degrees. And this should be the largest side. It should be larger than 10 when we evaluate that. So 7 times the sine of 107.2 degrees divided by the sine of 29 degrees. And sure enough, we get the largest side, so 13.8 units, roughly. So that is going to be our final side in this case. So that additional triplet of information represents our first triangle. And again, that resulted from the smaller value for B, the value that resulted directly from the inverse sine function. Now we need to solve for the other possible values of big C and little c, based on the larger version of B, the one that resulted by taking that inverse sine value and then relating it to something in the second quadrant of the unit circle. So again, we can solve for C directly based on the fact that we now have two angle measures. So C is equal to 180 degrees minus the 29 degrees we were given, minus 136.2 degrees, our value for B. So 180 minus 29 minus 136.2. And that's going to give me 14.8 degrees. So that's our value for C. So notice in the previous triangle, C was the largest angle. Now C is going to be the smallest angle, which means its opposite side is also going to be the smallest side. So it's going to have to be something that's smaller than 7 once we evaluate it. So using our ratio and then relating our ratio to our unknown, so sine of 29 degrees divided by 7 is equal to the sine of 14.8 degrees divided by little c. Solve for little c. So little c is equal to 7 times the sine of 14.8 degrees divided by the sine of 29 degrees. And so when we simplify that, plug that into the calculator, 7 times the sine of 14.8 degrees divided by the sine of 29 degrees. And we get about 3.7. So as expected, smallest angle, opposite smallest side. So 3.7 units. So this gives you an example of all the different situations you can run into using law of sines. And again, the hallmark of law of sines, when do we use it? Well, number one, we use it when we don't have a right triangle. So we no longer have a right angle in the triangle. We have what we call an oblique triangle. But specifically, we use law of sines when we're given an angle and opposite side pair, or we can directly solve for an angle and opposite side pair like we did in these last two cases. Now, what happens when we don't actually have an angle side pair? It's also possible we could be given information in such a way that there is not a possibility of directly solving for another angle and getting that pair. If we have a combination of information that doesn't allow us to directly use that side angle pair, we'll use a different rule, something other than the law of sines, what we call the law of cosines, and we're going to look at that in the next video.